Good afternoon.
Good afternoon.
All right, so we just have Hannah there, Jordan's not there, Skylar's there, but Chloe's not. And who's in St. John's today?
We're all here.
Oh, you're all there? Okay. Oh, there we go. Okay, thank you. Whoever adjusted the camera just then. All right, and anybody at White Mountain campus? No. Okay. All right. Well, so today our plan is to we want to finish 7.2 and then start in on 7.3. So let's see. So probably, well, I guess we'll wait and kind of see how that goes. But kind of what I'm thinking is for our first set of quizzes will be on next Wednesday. And so Monday and Tuesday, we'll probably talk about the times, what works for you guys. We'll kind of plan that out. And then we'll have a quiz on probably just 7.1 and 7.2. Just probably not 7.3, even if we finish it in time. We'll just kind of see how it goes. Now, I told you that I was trying to make it so that I could introduce a little bit more of a random element into the quizzes. And so, because I had several people say, it would be nice if you could work it out in such a way so that instead of the average score, we could take the highest score on the quizzes. And I'm going to tell you that it didn't look good until about 5 minutes ago. Anyway, I had a major breakthrough with the Moodle, and it finally started doing what I wanted it to do. So that's what I'm going to be tackling between now and class on Monday is and I'll try to let you know, but at least, so what to let you know what I'm shooting for is I want to make it so that, like, say when you take a quiz on 7.1, for example, that what it'll do is it will randomly choose from a bank of questions and scramble the answers each time. So that even though a lot of the questions will be the same, they might be in a different order, and they might not all be exactly the same. And so what that will mean is that there'll be enough random elements in there where I feel pretty good about that. It would be sort of silly, I think, to go through and just guess randomly on the first test, because that's what kind of drove me to do the average score, is that and I think that it would actually really encourage you to do to study for more. So anyway, I'm curious to see how it works out. But so then what we'll do is, if I can pull that off, is that we'll have so you'd still get 2 attempts, but you just get your highest score instead of the average. Okay, that's what I'm shooting for. All right, so I'll let you know how that goes. All right, any questions, comments, concerns before we get started today? Okay, well, let's jump in. We are, like I said, we're in 7.2 on part 3, the integral of the natural log. Okay, let's see. All right, so the first, we have the little formula there that you write in the notes. If u is a differentiable function that is never 0, then the integral of 1 over u du is the natural log of the absolute value of u plus c. Now, that formula we're going to use it so often, I would recommend that you memorize that one. So the integral of 1 over u, or sometimes you'll see it as the integral of du over u, which is the same thing. So it's the natural log of the absolute value of u plus c. Well, so usually what we do to integrate these is we do u substitution. All right, so if you remember when we did u substitution last semester, then what I told you is to pick for u whatever was in parentheses or under the radical or whatever. Well, for these, what you pick for u is typically what's in the denominator. At least that's kind of where we're going to start. All right, so here, so I'm doing the integral from 0 to 2 of 2x over x squared minus 5. So what I do is I pick for u whatever the denominator. So let u be x squared minus 5. And then so du, you take the derivative, 2x times dx. All right, now, so do you see here that we have the 2x dx, that's du. And then x squared minus 5, that's the u. So we've gone from an integral in terms of x to an integral in terms of u. Now, typically what I do at this point is I change the limits of integration. There's a way to do it without doing it where you substitute back, but I think it's easier to change the limits of integration. So here you say, okay, u is x squared minus 5. So if x is 2, 2 squared minus 5, that would be 4 minus 5, which is negative 1. And then if x is 0, 0 squared minus 5, that's going to be negative 5. All right, now we apply the formula. So the integral of du over u is the natural log of the absolute value of u. Now, you don't have to put the plus c if you have limits of integration. Okay, you don't have to, because the c's will cancel. Okay, so we're integrating from negative 5 to negative 1 now. All right, so now we've applied the formula, we've done the integral, so now we plug in and subtract. So you plug in the first number minus what you get when you plug in the second number. So that would be the natural log of the absolute value of negative 1 minus the natural log of the absolute value of negative 5. All right, now you apply the absolute values. And so we get the natural log of 1 minus the natural log of 5. Now, one of the rules for natural logs that we did earlier is that the natural log of 1 is 0. So whenever you see the natural log of 1, that's going to be 0. So we're going to end up with negative natural log 5. Or if you put the exponent back on the 5, 5 to the minus 1 is 1/5. So you would see your final answer as either negative natural log 5 or the natural log of 1/5. Now, if this were a test question, how could you check your work to see if you got it right? What could you do?
You could convert the ln 1/5 to like a decimal and then like go back. Yeah.
Okay. And then go back to what?
The original equation.
And then, so the original integral, and we could put that in our calculator, because when it's a definite integral, when we have limits of integration, your calculator can do this, okay? The problem is your calculator will give you a decimal. So then you would have to check your answer, because I guarantee you that the answer is not on a test is not going to be a decimal. but you might have one of these. So you have to make sure which is correct. Now on the guided notes, sometimes I'll say do the exact answers, which means I don't want you to put it in the calculator except to check it, because I want your answer to look like one of these, not a decimal. Okay? All right, so let's see. Go ahead and do practice 3A. So see if you can do that. I'll leave this example up for a minute and see if you can follow along. All right, Joey, when you've got it.
I got the natural log of 26, or 3.258.
All right, very good. So the exact answer is the natural log of 26. Okay? So any questions on that? Anyone like me to go through it? Okay. All right, very good. Now, you might remember, though, that sometimes when we do use substitution, we have to multiply by stuff on the inside and the outside to make it work. Okay? So in this example, when we go through and we say, okay, we're going to let u be the denominator, 3 plus 2 sine theta. But when we do the du, okay, the derivative of 3 is 0, but the derivative of 2 sine theta is 2 cosine theta d theta. That's what du is. So, but instead of 2 cosine theta d theta, I have 4 cosine theta d theta. So here's a trick, and I know we did this before, but it is another way instead of multiplying by number in front. What you can do is break up that 4 into 2 times 2. And so this 2 cosine theta d theta, that's just going to become my du. And then over u. This other 2, I'm going to pull in front. Oops. All right, now let's talk about these limits of integration again. Okay, so what we have to do is we want to change these limits. So you take pi halves and you plug that in for theta. So if pi halves, that's 90 degrees. The sign up there is 1. So 2 times 1 is 2 plus 3 is 5. Okay, do the same thing for the negative pi halves. So the sign of negative pi halves is -1. So -2 plus 3 is +1. So your limits of integration then are from 1 to 5. Okay? All right, so now we use the rule that we started off today. The integral of du over u is the natural log of the absolute value of u. We have the 2 in front. So 2 times the natural log of the absolute value of u. And so we're going to plug in 5 minus when we plug in 1. So now notice that both of these limits of integration are positive. So when they're positive, you can just drop the absolute value because the absolute value of a positive is just a positive. So we don't have to fool with the absolute value. So you just say natural log of 5 minus the natural log of 1. And then remember the natural log of 1 is 0. And so my final answer is 2 natural log 5. All right? Any questions? All right, so go ahead and try practice 3B. And I'll leave this one up for a minute. All right, Joey, when you've got it.
Okay, so I got 5 natural log of 7.
Okay, so let's see, I got 5/3. So let's see where the third comes from. Oh, okay. So you see on this one, so if you let the denominator be u, then the du is 3 cosine x dx. Okay? See, so you don't have a 3 up here. So what you need to do is you need to put a 3 up there. Pull the 5 in front. So by putting a 3 in there so that we have 3 cosine x dx, you have to put a 1/3 out front to compensate for that. So then when you pull the 5 out front, you already have the 1/3 out front. So you already have 1/3, and so it's going to become 5/3 out front. Okay, does that make sense, or do I need to go through that again?
No, it's good.
Okay. All right, other questions on that one? All right. All right. So now, you remember when we did integrals, when we introduced integrals, we only integrated the sine and the cosine. Okay, and I think somebody said, well, what about the integrals of the other trig functions? And I said, well, we'll get to those another day. Well, so this is the day. The reason why we had to hold on is because the other 4 trig functions, their integral involves the natural log. So we had to wait till chapter 7 with natural logs to have these in. So the other trig functions. So you can just write these down. The integral of tangent, and you can use x's or u's, it doesn't matter. I usually use x's in the formula, but anyway, the book uses u's. But it's the natural log of the absolute value of secant u plus c. The integral of secant u du is the natural log of the absolute value of secant u plus tangent u plus c. The integral of cotangent u du is the natural log of the absolute value of sine u plus c. And the integral of cosecant u du is negative natural log the absolute value of cosecant u plus cotangent u plus c. Okay, so let me show you where this comes from. Okay, you don't have to know this or whatever, but I'm going to show you why they involve natural logs. Okay, so let's start with tangent x dx. So if I rewrite this as sine x over cosine x, then once again, if I take the denominator to be u, let u be cosine x, then du, the derivative of cosine, is negative sine x dx. So then what I need to do is multiply by a negative in front. So I have negative sine x dx. I mean a negative inside with the sine and then a negative out front. So then I end up with the negative of du over u. And so then that becomes the negative natural log of the absolute value of u. Okay, here, let's show that through in that step. So negative natural log of the absolute value of u plus c. And then substituting what u was, negative natural log the absolute value of cosine x plus c. Now, a lot of times you'll see that integral written like that, or since the negative, if you put that as an exponent on cosine, 1 over cosine becomes secant. And so either of these you might see as a definition for, or as the integral of tangent. Okay? And so that's kind of how you derive these formulas for the integral of the other trig functions using logarithms, is you try to make it into a du over u situation. Okay? Any questions on that? All right, let's just move on. Okay, so now in this next example, what I want to do is use one of those formulas, show you how to use the more complicated formulas. So for this one, for example, we want to integrate the tangent of 2x, okay? If it was just x, we could apply the formula. We also have limits of integration here, so we'll deal with that. So what I do is let u be whatever the argument of the trig function is. So if it's 5x, let u be 5x, or if it's square root of x, whatever. Whatever the argument is, let that u be that. Okay, so then du would be 2 dx. All right, so now what I need is, so this would be the tangent of u, so the tangent of u, and then I need a 2 with the dx to make it du. So I multiply by 2 to be with the dx, and then I multiply by 1/2 to compensate for it. All right? So now I change the limits of integration. So if I plug this in for x pi 6, well, u is 2 times that. So 2 times pi 6 is pi thirds. But 2 times 0 is still 0. Okay? So now I have it set up as the integral of tan u du. So now I use the formula, one of the formulas that I just gave you, and say, okay, that's going to be, I'm going to use this one in red. Okay, so I'm going to have 1/2 times the natural log of the secant of u. Okay, so u was 2x, so the secant of 2x, and then I'm going to evaluate that from 0 to pi thirds. Those are my limits of integration. Okay, so now this is the order that you apply the arguments. You plug in these numbers for x, multiply it by 2, then take the secant, then the absolute value, and then the natural log, and then multiply by 1/2. Okay, so that sounds a lot worse than it really is, but so plug in the pi thirds. So 2 times pi thirds is 2 pi thirds, and then 2 times 0 is going to be 0. All right, now, so to figure out the secant of 2 pi thirds, what you want to think of is what is the cosine. Okay, so 2 pi thirds, what you do is you think of what's the cosine of 2 pi thirds. So you can look it up in your unit circle or whatever. Cosine is going to be negative in quadrant 2. And so pi thirds up, that's going to be at 1/2. So the reciprocal of that is going to be -2. Okay, the secant of 0. So we think, well, what's the cosine of 0? The cosine of 0 is 1, so the reciprocal of that is also 1. All right, now you apply your absolute values. Here, I guess let's go ahead and keep the absolute value sign here for one more step. The absolute value of -2 is 2. The absolute value of 1 is 1. But the natural log of 1 is 0. So then what we end up with is 1/2 times the natural log of 2 is our final answer. Oops. Okay, so that was kind of a long problem with the U substitutions and so on. But let's see if you can do practice 4. All right, Hannah, do you have it?
Yeah, I think so. -1/2 natural log √3/2.
Very good. All right, would anyone like me to go through it? Wow, you guys are awesome. Okay. All right. Okay, so the last thing on this section is what's called logarithmic differentiation. Okay, it's a process of using logs to simplify before differentiation. There's some problems that would almost be impossible to do without this method. Or they would actually be extremely difficult. I mean, you could do it. Okay, so now here's the thing, though, is while I think this process is fairly straightforward, I mean, especially the more comfortable you are with logs, the easier this is going to be. I will warn you, these problems require a lot of writing, okay? A lot of writing. So on this example that I'm going to show you, I don't want you to write it down, okay? Because we'd spend the rest of the period just writing it down. So I want to spend the rest of the period having you do the practice problem. So, but before you jump in, I want you to just watch, okay? And watch a logarithmic differentiation, okay? All right, so here's the deal. If we want to take the derivative, okay? Well, that's Calc 1. We know how to do that. But see, here's the problem, is that in order to do this derivative like we did in Calc 1, we would have to use the quotient rule. And then inside the quotient rule, we would have to use the product rule. And then inside the product rule, we would have to use the chain rule. And so by doing logarithms, it's actually going to make it so that we don't have to do any of those. Okay? So you'll kind of see. So the first thing we do, in fact, is we take the natural log of both sides. So you just write ln of one side equals ln of the other side. Okay? Now what we're going to do is use the properties of logarithms to break this down to pluses and minuses. Okay? So the log of a quotient is the log of the numerator minus the log of the denominator. Okay? So that step right there is made it so we don't have to use the quotient rule. Okay? Next, we have the log of a product. The log of a product is equal to the sum of the logs. So we have the log of x squared plus 1 plus the natural log of x plus 3 to the 1/2. So what we just did there is made it so we don't have to use the product rule. Okay? Now we use another property of logs that says if you have a log raised to a power, you can bring that power in front. And that little step is going to make it so we don't have to use the chain rule. Okay? So those three steps basically made our life much easier. So now what we do, so we took the log of both sides. And so now what we're going to do is take the derivative of each side. So that's the whole point, is to find the derivative. So the derivative of the natural log of y is 1 over y dy dx, because it's a different variable. All right, now, so we learned in this section that the derivative of a natural log of blob is 1 over blob times its derivative. So, and so the derivatives of these natural logs are easy once you do a few of them. So it's 1 over x squared plus 1, and then the derivative of x squared is 2x. All right, then you bring down the half. The derivative of natural log of x plus 3 is just 1 over x plus 3, minus the derivative of natural log x minus 1 is 1 over x minus 1. Now, we're not going to get common denominators. We're not going to add those together or any of that nonsense. The only thing I'm going to do to simplify this is probably put the 2x up top. All right, now, let's see. Do we do that? Okay, so now to solve for dy dx, the derivative, what we do is we multiply both sides by y. Well, now what's y? Well, y is all of this mess right here that we started with. And so when we multiply each side by y to get dy dx by itself, okay, then in place of where this y, what this y is, I'm just going to write the original problem. So all of this is y times the derivative of each of those. Okay? So again, that's an ugly answer. I get it. I know it's long, but it really isn't that difficult, but it's just a lot of writing, okay? So let's just see how you do on practice 5. So I'll scroll up so you can kind of remember how to get started. All right, so Joey, whenever you've got it. Or if you get stuck, let me know.
Okay, is it 1 over x, then x plus 2 and x plus 3, and then in parentheses, negative 1 over x minus 1 over x 2, or plus 2, minus 1 over x plus 3.
Okay? I think that sounds pretty good. So let's just, we'll just double check the signs here. Now, because it's 1 over, when you break those up as a natural log, see it's the natural log of 1 minus the natural log of all of those. And so you can either leave the negative in front because this becomes 0, or you can distribute it through. So some students like to do it either way. So either make each of these terms negative or put the negative out front, okay? And so so then when you multiply by y, okay, so this was our original y. So whoever did this put the -1 with the y and then left all of these positive. But if you distributed the negative through, your signs might be negative in here. So I can't remember if you had those signs right, but I think everything else is good. Did you have the signs okay?
Yeah, I left it out front.
Okay. All right. Any questions on that? Yeah. So when you have the natural log of 1 is 0, you just kind of have to remember that's going to go away anyway. Okay. All right. So good job. You know, big ugly answer, but it's really not that bad. Okay. All right. Well, that's it for 7-2, and that's a good place for us to stop. So, any questions, comments, concerns before we call it? All right. Well, you guys have a great weekend, and we'll see you on Monday.